Hello again. In the previous lesson, we studied geometric sequences and series. In this lesson, we're going to bring those two ideas together and then also introduce something called binomial theorem. All right. We will classify patterns, find terms and sums, and use Pascal's triangle and even identify binomial coefficients. Okay. So first of all, we need to begin with the quick rules. When it comes to arithmetic patterns, they have a constant difference, okay? So a constant difference, or D is equal to C with respect to the arithmetic, okay? So there's a constant difference, then it would be the arithmetic pattern. With respect to geometric patterns, they have a constant ratio, okay? So the ratio would be the constant, okay? So again, with respect to geometry, you have a ratio, and then with respect to arithmetic, there's a constant difference. So D is equal to C, or the ratio is equal to, essentially, I say a constant. And it could be used as a constant, which we'll leave it at that. Some people write it as A over B, but it's still the same thing. All right, so use A sub n for a term and S sub n for a sum. So if you're looking for a specific term, you're going to use the arithmetic sequence. If you're looking for the sum, you're going to use the summation formula. A binomial theorem expands powers as a plus b raised to a power of n, and then Pascal's triangle provides coefficients for small binomial powers. All right. So let's first of all classify each one of these. We have sequence A and sequence B. I can look at these and see that there is a pattern with both of these. So for A, I see what's happening. We have 14 minus 9. Then we have 19 minus 14. Then we have 24 minus 19. And so it just so happened 14 minus 9 is going to give me a difference of 5. 19 minus 14 is going to give me a difference in 5. And then 24 minus 19 is also going to give me a difference of 5. So I know that the difference here is 5, and then this is arithmetic. Okay. Now let's look at B, the sequence for B. So looking at these terms, I can essentially say, okay, 27 over 81, that's going to drop down to 1/3. And 9 over 27 is going to drop down to 1/3. And then 3 over 9 would also drop down to 1/3. So we have 1/3, 1/3, 1/3, indicating that we have a ratio of 1/3. Also indicating that this one is geometric. Okay, let's continue. Example number 2, it says find a sub 15 for the arithmetic sequence with a sub 1 equaling -4 and d is equal to 3. So we're already told that we're looking for the arithmetic sequence. So that tells me that I'm looking for one particular term. So I'm going to use a sub n equals a sub 1 plus n minus 1 multiplied by d, okay? And I already know some things about this. So I'm looking for a sub 15, which in this case is going to be a sub n. Then I'm also looking for a sub 1, or excuse me, I already have a sub 1, which is -4, and then I also already have d, which is 3. So I'm just going to plug those values in. So a sub n is going to be a sub 15 equals -4 plus n, which is 15, minus 1 multiplied by 3. -4 plus 14 times 3. That would, 14 times 3 is going to give me 3 times 4 is 12, raise the 1, that'll be 42. So -4 plus 42. So a sub 15 is going to be 38, right? So find a sub 15 for the arithmetic sequence. Checkmate. All right, pause and try the problem below. All right, so this one says find the sum of the first 6 terms of 7, 14, and 28. Okay, so first of all, I can look at these terms and see that there's a ratio happening here. So we have 14 divided by 7, which is 2. Then we have 28 divided by 14. That's also 2. So the sequence is geometric, right? So this is a geometric, okay, where r is equal to 2, right? So we do know the first term. We know a little bit about this already. So we have, we're looking for, it says find the sum of the first 6 terms. So we're looking for um, essentially a sub 6. A sub 6 is going to be a sub n in this scenario. And then we also have a sub 1, which is 7. And then we also know that the ratio is going to be 2. So we can use S sub n equals a sub 1 multiplied by 1 minus r raised to the power of n, 1 minus r. Okay, just make sure you don't make any mistakes with this, because I'm actually looking at 2 screens, which is why there appears to be a good bit of mistakes in my videos. But here, what we're doing is S sub n equals a raised to the first power multiplied by this expression here. So again, we're looking for the 6th term. So this will be a sub 6. And remember, n is going to be equal to a power of 6. So a sub 1 is going to be 7. So it's going to be 7 times 1 minus r. R is 2 raised to the power of 6 divided by 1 minus r, which is 2. So just make sure you revisit so you know what you're substituting in here. So 7. And then, of course, what we're going to do is we need to find 2 raised to the power of 6. 2 raised to the power of 6 is 2 times 2 times 2 times 2 times 2 times 2. So 2 times 2 times 2, or 2 raised to the third power, I know is 8. And then doing that again is going to give me 64. So 2 raised to the power of 6 is going to be 64. 64 minus, or 1 minus 64 is going to be a negative 63. And then 1 minus 2 is going to give me a negative 1, which simplifies to 7 times 63. So s sub 6, and then s sub 6 is going to be a total of, let's see, 7 times 3, that's 21. 1 carry the 2, 42 plus 2 is 44. That's 441. So S sub 6 is 441. We can check by listing the 6 terms as well. So essentially that would be 7, 14, 28, 56, 112, and 224. Notice, so the ratio is 2, so it's just 7 times 2 would be 14. 14 times 2 is 28. 28 times 2 would be 56. 56 doubled is 112. 112 doubled is 224. Okay. And then if we added all those up, we would end up with 441. So just to show you that this rule or this system checks out. All right. Let's continue. Example number 3. Example number 3, we're going to be using Pascal triangle to expand x parentheses x plus 2 raised to the third power. So the exponent is 3. Remember, this corresponds to a plus b raised to the power of n. Okay. So what this essentially is saying is Pascal's triangle coefficient for the power of 3. So it's essentially saying 1, 3, 3, 1, right? Pascal's triangle coefficients for the power of 3, right? So the exponent is 3 for this expression. And so essentially we're going to use the row of Pascal's triangle for the third power. And I'm going to show you what that looks like here in a second. Okay, so if you've never seen Pascal's triangle with respect to this, then I'll show you how it works over here. So suppose if you have, so this expression here is basically you have a plus b raised to a power of a value, right? So let's just say we have a plus b raised to the power of 0. Well, that's just going to be 1. And then let's say we raise that a plus b raised to the power of 1. So what that's basically saying is that 1a plus 1b. And then if we did a plus b raised to the second power, then that's essentially 1a squared plus 2ab plus 1b squared. So what you're doing is you're taking the expression and squaring it, taking the expression, raising it to a power, taking the expression, raising it to a power. So whatever the number is you're thinking of, you would essentially use that value. So here we're using a plus b cubed, which is the same as a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay. So when it says use Pascal's triangle to expand x plus 2 cubed, notice n is cubed. So what I'm doing is I'm using the coefficient here is 1. The coefficient here is 3. The coefficient here is 3. The coefficient here is 1. So that's where those values come from. Now we need to determine the power of x. So the powers of x begin at 3 and decrease to 0. Okay, so essentially that would be x cubed, x squared, x to the power of 1, x to the power of 0. The powers of 2 begin at 0 and increase to 3. Okay, so again, this value, the powers of x begin at 3 and decrease to 0, right? And then the powers of 2 begin at 0 and increase to 3. So that's essentially 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, and then 2 raised to the power of 3. Now what we do is we combine the coefficients and the powers. Okay, so using that information, x plus 2 raised to the power of 3, that would be 1x cubed, right, times 2 raised to the power of 0 plus 3x squared raised to the power of 2 raised to the power of 1 plus 3x to the power of 1, or just 3x, multiplied by 2 squared. And then finally 1 x to the power of 1, x to the power of 0, which is essentially 1. And then that would be multiplied by 2 cubed. Okay. And then now we can simplify each term. Okay. So 1x cubed times this is just 1, because 2 raised to the power of 0 is just 1. So this will be just x cubed, right? We don't have to write that 1 in front of it. And then 3x squared times 2 to the power of 1 is essentially 3x squared times 2, which is going to be 6x squared. 2x times 2 raised to the power of 2, that's 4, and then 3, so that would be 12x. And then 3 or 1 times 2 cubed, that's 8. So 8 times 1 is just going to be 8. So the final answer of x plus 2 raised to the power of 3 is x cubed plus 6x squared plus 12x plus 8. Okay. And this is just a super fast way to compute expressions like this that are raised to a high power. Okay. You know Pascal's triangle off the top of your head. That is the fastest way to compute these problems. Okay. All right. Example number 4. Find the middle term of x plus 1 raised to the 4th power using binomial coefficients. So the 4th power uses the following row of Pascal's triangle. All right, so the following row of Pascal's triangle, if we continued on, would be 1, 4, 6, 4, 1. Okay, so a 4th power expansion contains 5 terms. Okay, so just like if it was raised to a power of 0, it'd just be 1. Raised to the power of 1, it would have 2 terms. Raised to the power of 2, 3 terms. Raised to the power of 4 terms. Okay, 1, 2, 3, 4, and then and if you have 4 terms, then you'll have 5. Okay, so the 4th power expansion contains 5 terms. The middle term is the 3rd term. Okay, this term is the 3rd term. So, for example, if we have the problem here, x plus 1 raised to the power of 4, we can essentially write that as 1 x to the power of 4 plus 4 x cubed parentheses 1 plus 6 x squared times 1 squared plus 4x 1 raised to the power of 3, and then plus 1 raised to the power of 4. And then we simplify. So we simplify this expression, which would be x to the power of 4 plus 4x cubed plus 6x squared plus 4x plus 1. Okay. The 3rd term is the middle term. Okay. So it says find the middle term of this. So the 3rd term is the middle term. That middle term would be 6x. Okay. 6x squared. We do not need to focus on every term to answer the question, but writing the expansion makes the middle term easier to identify. Okay. Common mistake. A student uses an arithmetic formula for a geometric pattern. Explain how to check the pattern before choosing a formula. Before choosing a formula, we need to test the sequence, which is to first calculate consecutive differences. Okay, so an arithmetic check is this. Is essentially second term minus the first term. Okay. And then the third term minus the second term. And then so on and so forth. If the differences are constant, then the pattern would be arithmetic. That's how you check the arithmetic. If the differences are constant, okay, so a constant difference, then that would be arithmetic. Okay. Geometric check is this. The geometric check is the second term divided by the first term. Okay, that'd be the first thing, and then you would do the third term divided by the second term, and so on and so forth. Okay, and same thing here, so on and so forth. If the ratios are constant, the pattern is geometric. Okay, so the ratio. Okay, would be geometric. All right, just keep that in mind. So, for example, if we have if we have 2, 5, 8, and 11, right? That has a constant difference of 3, right? So we have going from here to here, here to here, or excuse me, we'll say the second term and the first term. So that's 5 minus 2, 3. 8 minus 5, 3. 11 minus 8, 3. So notice there's a constant difference of 3 there, right? Then what if we had the numbers 3, 6, 12, and 24? Well, we would take 6 divided by 3, that's 2. Then we would take 12 divided by 6, that's also 2. Then we would take 24 divided by 12, which is also 2. So the ratio of these values, or the ratio of their respective numbers, taking the second term divided by the first term, the third term divided by the second term, and the ratio being consistent, that lets me know that there's a constant geometric ratio there. Do not choose a formula simply because the numbers increase or decrease. You can't do that, okay? You have to check how they change. All right, so the final review is this. So again, with respect to arithmetic, there needs to be a constant difference. With respect to geometry, a constant, or excuse me, a ratio that is constant, okay? When you're looking for a singular term, only use the a sub n. When you're looking for the sum, you want to use s sub n, all right? The binomial theorem expands powers as a plus b raised to the power of n. And so what you can do is review Pascal's triangle and see what happens if it's raised to a power of 0, if it's raised to a power of 1. And then you look at what those coefficients are, because Pascal's triangle provides coefficients for small binomial powers. And so those things are pretty consistent, okay? All right, so this completes video 16, part 4, sequences, series, and binomial theorems. Thank you for watching, and I hope to see you in the next one.